Let's try again.
Okay.
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 Okay. Thank you, Professor Tanaka. Now,
Yeah,
Professor
thank you.
Zhang, please. Okay.
Can you see my PPT?
Okay. Now,
Can you see my PPT?
okay.
No, the previous one was better.
Oh, thank you very much. Good morning, dear Professor Kova, and the organizing committee, colleagues and friends. Colleagues, I'm Hengchang Zang from School of Pharmaceutical Science, Shandong University. It is an honor to be able to participate in this conference. The topic of the report I brought today is understanding hyaluronic acid-induced variety of water structure by near-infrared spectroscopy. This is the content. The topic of in copy of the present include the background of hyaluronic acid, why we made research on it, our recent research, and outlook of the future works. Hyaluronic acid is an inherent substance in our body. I believe most people are not unfamiliar because now it is widely used in cosmetics, healthy food, and medicines. In Japan, we often see its related products in supermarkets. It presents in most organs and connective tissue, and its metabolism is very fast, with a half-life in tissue of 0.2 to 1.5 days. 0.5 to 1.5 days. It has strong ability to bonding water. The theoretical capacity of HA to retain water is reported to be between 2 to 6 liters per gram. And the molecular weight of HA, the rate of viscosity of the solution. Different viscosity of HA has different pharmacological effect, and its viscosity change with pH. HA is disassembled and visco decline when treated with enzyme acid or with a reducing agent in the presence of metallic ions. In the aspect of pharmaceutical effect of HA, it is able to retain water in extracellular matrix formed in the gaps between cells. It exists in the joints as a lubricant to reduce friction resistance between articular cartilages. As we mentioned, HA is now widely used in many products, and in China, it is just approved in common food, so it has a big market. Water is the major chemical component in our body. We can see from its finger. With increasing age, HA contained within the body is decreasing, followed by the water decline in our body, and at the same time, studies have shown that there is a close relationship because these two. HA and water are closely related in the realization of the biological functions. Since the realization of HA function is closely related to water, however, how is it related? Can we research on the changes in water structure caused by HA guide its application? For example, in cosmetics, how are the film forming properties related to high molecular weight and how the permeability related to low molecule weight. Near-infrared aquaphotometrics is just suitable for this kind of research. The purpose of this study is to continue and extend the research on the hydration behaviors of HA. And particular attention is paid on investigating the water structure changes induced by HA. In the category of aquaphotometrics, Professor Chinkova analyzed the information of water molecules in a large number of aqueous systems and established a concept of water matrix coordinate, which is of great benefit to our research. Thanks for Professor Chinkova. This table is the basis of the subsequent analysis of this study. Here is the whole content in this study. Here are the materials and methods. We analyzed the HA solution in the range of 1 to 100 milligram per milliliter using near-infrared spectroscopy with different temperature. The decrease in the intensity with increasing HA concentration in figure 1. The original spectrum could be explained by the reduction of water. Furthermore, as the temperature increased, the peak around 7,000 inverse centimeter shifted to high frequency. The indices of the 3 water species S0, S1, and S2 in figure 1D. Second, derivative spectra changed with increasing temperature, indicating the temperature had the effect on water structure. The calculation of the absorption value in the region we calculated in figure 2 proved the non-linear decrease behavior of HA aqueous solutions. The reason for the decreasing generally comes from 2 possibilities. One possibility was the HA absorbed less NRR light than water in the OH stretching ring, and therefore an increase in the concentration of HA would result in the decrease in absorption. It can be considered that though HA has a long chain structure, its contribution to NRR absorption is different from that of pure water. Another possibility was that water molecules were affected by HA, which finally changed the molecular vibration. If the change was entirely caused by the absorption of HA, the absorption value should be linear with HA concentration. Therefore, the change should also came from the third substance, that was the contribution of hydration water. PHA was performed on HA concentration depends NIR spectrum. The score of the first component in figure 3 was simply a straight line, suggesting that the spectral changes extracted by the first component varied linearly over the entire concentration range. mainly reflecting the degrees of water. The score vector was parabolic with a top precision of 40 milligram per milliliter, which indicated that the spectral changes captured by the second loading and undergone transitional change around this concentration. This indicated that the loading plot of the second principal component reflected the hydrogen bond change of water caused by the increase of HA concentration. In order to further investigate the water structure change caused by HA, the reconstructed spectra from the first two principal components are calculated. Then a radar chart was established to visualize water spectral pattern at a different concentration. As a result, quite a characteristic water absorption pattern was biased towards the low frequency range, which increasing HA concentration, indicating the transformation from less hydrogen bonded water structure to more hydrogen bonded water clouds. The intensity variation of each water species in Figure 4 was shown in Figure 5. We can see that when the HA concentration was lower than 40 milligram per milliliter, only the formation of S4 was promoted, probably because HA is a long-chain polysaccharide rich in OH. It can directly combine a large number of water molecules into a tight network structure. The addition of a low concentration of HA may promote the conversion of S1, S2, and S3 into S4. The strongly hydrogen bonded water species, however, as the concentration was further increased above 40 milligram per milliliter, S4 continued to increase. With more HA molecule began to promote the formation of S2 and S3. When HA concentration was lower than 40 milligram per milliliter, the strong hydrogen bond water structure was preferentially formed. And when the concentration continued to rise, the medium hydrogen bonded water network began to form. Moreover, it is being found that in the dilute solution, HA behaves as a stiffened random coil. When in concentrated solution, stiffened random coils showing entanglement. In order to further explore the HA effect on water structure, PCA was performed on spectral data of HA solution at different temperatures. Figure 6 showed the first two loading and score of the spectrum of 100 milligram per milliliter HA solution from 25 to 55 degrees. The first principal component explained 99.8% of the total spectral variance, and its loading was dominated by a positive peak at 70-91 and a broader negative peak certain at 67-25. with a very thin exploitation of 99.8%. The first principle company can be considered to explain all spectral changes of importance. The second principal component accounted from 0.16%.
Professor Zhang, maybe it's better to faster. We have no time for the coffee.
Okay. The second principal content account from 0.16% of total vision, although is loading sold domical period peak at 70-18. Maybe I can next. In order to get more information on what structure changes with temperature in the HA solution, the reconstructed spectra from the first component were calculated as figure 7. Based on the reconstructed spectra, the radar chat showed part of character tint the options was biased towards to the high frequency, indicate the dissociation of water cloud and the formation of less hydro-bound water structure. Then we compared the changes of water structure in HA solution and pure water at different temperatures. And the peak insisted of S0, S1, and S2 in figure 8. In conclusion, HA can bind different water species at different concentrations and different temperature. It acted as a structure mark to make water molecules arranged in order. It had the ability to improve the thermal stability of water structure, suggest a potential bioprotective function. HA with this molecular weight has been proven to repair skin damage caused by photoaging, and we are also working with Blumig company, the biggest HA producer in the world, to investigate whether it is due to the protection of water structure by HA. Aquaphotomatics provides an unique perspective on the molecular interactions between HA and water molecules, which is helpful for understanding the role of HA in life process and may serve as the basis of HA application. HA forms a large number of intermolecular and intermolecular hydrogen bonds in the water environment. When the external conditions change, the intermolecular interaction made changes immediately. Exploring the spectral conditions of HA bound to water molecules in a specific environment is of great significance for precise medicine. Therefore, study and understand the interaction between HA and water in a complex environment will deeply understand the issue reason for HA to export its biological activity, and it will also be a great benefit to development and use HA products. In short, regardless of the physical and chemical properties, functions, and the uses of HA, the role played by water molecules can't be ignored. For the analysis of current situation, aquaphotometrics is an invaluable tool. That's all. Thank you for your attention. and welcome to visit our lab. I believe we have a lot resonance with water, a small molecule, but reflecting a big world. Thank you very much.
Okay, thank you, Professor Zhang. Thank you for the interesting talk. I think we have used all the time for the coffee break, so maybe we have discussion later. Now it's the time for the next session. Now we close this session. Okay, thank you. Bye.
Thank you, Professor Shao. Thank you for sharing the session. I would suggest to have just 5 minutes. Let's start the next session. Now is 10:43 Japanese time. Let's start 10:50. Sorry about this, but we really need some air. Okay. Professor Takeuchi, I'm sorry for that. So please, so we move from 10:40 to